So we just saw how to use the wavelet tree to have something like an index for the Boroswheeler transform to allow us to reverse it efficiently. Now we want to see how to use the wavelet tree in order to answer queries that are full text index type queries like locate and count, and in particular we're going to start with count. I'll have a few things to say about locate at the end. Okay, so how do we answer this count query? We have a text, we have its Boroswheeler transform, and we have a wavelet tree over the Boroswheeler transform. And we'd like to know, for a given pattern string, p, shorter than the text, how many times does the pattern occur in the text? At how many offsets does the pattern occur in the text? Okay, so let's consider our Boroswheeler matrix. We've seen this many times now, our Boroswheeler matrix here for ABA, ABA. And we've got our first column, we've got our last column, which is the Boroswheeler transform. And let's observe a couple things about the matrix. So first of all, rows that have the same prefix are consecutive. So what I have here highlighted are the two rows that start with ABA. Right, so I've drawn my rectangle around the two ABAs that are at the beginning. And because the entire matrix is sorted, it's all the rotations in alphabetical order, we know that rows that have the same prefix will be consecutive. This is going to be convenient because it means that at any given moment in our algorithm that's going to be doing pattern matching, we can describe the part of the matrix that starts with the query that we've matched so far. We can describe that part of the matrix with just two numbers, right? The interval, the collection of rows that start with the query matched so far. So that's going to be very convenient. And in fact, this is a pretty profound idea. And when we get to Wheeler graphs, we will generalize this idea and continue to use it. But here it's very important because what it means is that at any given point, we really just need an interval to describe what we've matched so far. The other observation is that if you look in the last column of those rows, right, so if I have the rows that start with ABA highlighted here, then of course what I can see in the last column for those rows is the characters that come just before those occurrences of ABA. So one of those occurrences of ABA is preceded by A. And one of those occurrences of ABA is preceded by $. Okay? So the rows that have the same prefix are consecutive, and then if we look in the last column of those rows, what we're seeing are the characters that come before. Let me now show you the matrix again, and as we did in a previous lecture, I'm going to put subscripts on the characters in the first column and in the last column. This time the subscripts are just going to be ascending order with respect to these two columns, right? So like the first A gets rank 0 and the second A gets rank 1, etc. Okay? All right? So these subscripts are ranks with respect to L, right? This is the A of rank 2 because there's 2 A's before it in L. This is the A of rank 3 because there's 3 A's before it in L. Okay? So if we're given some pattern P, I've got a nice short example here where our pattern is ABA of length M. The process we're going to go through is going to be a process of matching longer and longer suffixes of the pattern. So we're going to start with the shortest suffix, just A in this case, and we are going to discover which are the rows that start with that suffix, and then we are going to proceed iteratively to find a new range of rows and a new range of rows, and each new range of rows is going to be the rows that start with a longer suffix. We're going to start with short suffixes and work toward longer suffixes. But the invariant, the thing that we're achieving at each step is we're finding the range of rows of the matrix that start with the suffix so far. Okay, so our first task, right, the smallest suffix here is A. So our first task is to find all the rows that start with A. And if we have pre-computed how many, we have this array C that we discussed from the lecture about reversing the BWT with the wavelet tree that just basically counts how many characters are there in T that are alphabetically less than the query character. So if we want to know what are all the rows that start with A, we just want to know, well, what's the row where we can find the first A, and then what's the row where we can find the first C, since that's the next character after A, or B in this case, sorry, the first B, since that's the next character after A alphabetically, right? So we just want to ask, we want to do 2 lookups in that array to find the range of rows, which will be the first range, the range of rows that start with A. Okay, I'm drawing the range here as 1, 5, but with a square bracket here and a rounded bracket here, because it's exclusive at the high end, right? So it includes 1, but it does not include 5. But it's going to be convenient still to express it as 1 to 5. Okay. All right. So success. So we've matched that shortest suffix, the one that consists of just A. So now let's keep going. So here's our progress so far, right? This is the range of rows that start with A. And we said we could describe that range of rows like 1, 5, right? Now we want to find the range of rows that start with BA. Okay? The next suffix longer. So how do we do that? Well, we want to look again over here, right? We have our range of rows that start with A. Now we want to look in the last column in those rows, because what we see there are the characters that precede all the A's in the text. So if we look over here, we discover something interesting, which is that 2 of these A's are preceded by B's. And so those B's are B's that are just before A's, and therefore those are the rows we want to go to next. We want to go to the rows that start with B's that come just before A's. So which rows are those? Well, they're the rows that start with those B's, the B's of those ranks, 0 and 1. All right, so the B0 and B1, the B of rank 0, the B of rank 1, those specifically are the B's that come before A's. So we want the next range of rows in the Boroswheeler matrix to be the ones that start with the B of rank 0 and the B of rank 1. So which rows are those? Well, we can see them down here. So we want that to be the next range. Okay? And we know we can do this because once we know that the B's here are the B of rank 0 and the B of rank 1, we can use the LF mapping to figure out where they are, right? We can use a combination of a rank query and a lookup in the C array to figure out which are the rows that start with the B of rank 0 and the B of rank 1. We'll step through that process in a moment, but we can remember from the previous video that that's something that we can do. Okay, so now I have all the rows starting with BA in the Boroswheeler matrix. On to the final step, which is that I want to find all the rows that start with ABA. So I just do the same thing again. Again, I'll look in the last column in the rows, and I'm going to look for A's, and in this case I find them, right? Both of them are A's. So what that means is that the rows that start with ABA are the rows that start with the A of rank 2 and the A of rank 3. Right? So I can use the LF mapping to figure out what those rows are, and then that's the final range. Those are the rows that start with ABA. Right? And this range, the way we described it before, I could put 0, 1, 2, 3, so we could describe it as 3, 5. Right? Okay, so now we have the rows that have ABA as a prefix, and we were trying to answer this count query, right? So what's the answer? Well, it's just 5 minus 3. It's just the number of rows in my range, which is 2. Okay, so now that I have the rows that start with ABA, it's a simple matter of figuring out, of doing a subtraction to figure out how large that range is to find the answer to the count query. The answer is 2. Okay, so that's the idea. Now let me show an example where the pattern actually does not occur in the text. Right, I'm going to show what it looks like when the query essentially fails, or when the query should return 0. So in this case, what happens? Well, let's say our pattern, instead of being ABA, was BBA, but we keep the same text. So BBA does not occur in the text. So where would we, at what point in the algorithm would we discover that BBA does not occur in the text? Well, here are the rows. We would get to this point. Everything would work just fine up to here, where we have the range of rows that start with BA, this suffix. But now we would go look over here and we'd discover that there's no B's, right? And so that would be when we would have learned that the pattern BBA does not occur in the text. Okay? Another way to think of that is that the answer from that query would be like a range where the two indexes are the same, right? You know, if we had like 2, 2, right? That means there's nothing in that range, right? So the range that comes out of one iteration of this algorithm can be empty. Okay, so that's how we're going to do it. That's the process. We'll do it in a detailed way using rank queries in a moment. But first, we need to figure out exactly how it is we do this process of looking in the last column and seeing what's there. What we don't want to do is we don't want to scan. What we've been doing with our eyes, looking at these examples, is we've been scanning all the characters that are there in the last column corresponding to the range. But in general, the ranges might be very large, right? The ranges might, you know, even, for example, if the pattern occurs many, many times and the suffixes of the pattern occur many, many times, we might have a pretty large range. And we'd really rather not just scan all the characters in the range. Rather, we'd like to be able to use rank queries to answer the question how many and which A's or how many and which B's are the ones in the last column corresponding to this range. So let's just think about how to do that. I'll bring back the example from when we introduced the Boroswheeler transform, because this was an example that had a large text. Okay, so say we have some large text. And so again, I'm showing you here, this is a sort of extract from the Boroswheeler matrix where I'm taking the first several columns for a range of rows. So you can see that these are sorted, right? These are in sorted order alphabetically, everything in the blue box. And then the red rectangle has the characters in the last column corresponding to those same rows. So in other words, the characters that come just to the left with respect to the original text. So I actually don't need the blue stuff. So let me hide that. I don't need this diagram either. My question for you is, let's say I were to take this part of the L column, the Boroswheeler transform. I was going to take this part and just hide everything except for the beginning and the end. And we were going to try to answer this question, which is the same type of question we've been asking. But so far we've been answering it by scanning visually across this whole set of characters. So like, what are the E's that are in this range? So let's answer that character. What are the E's that are in that range, but with rank queries? So the way we would do that is we do 2 rank queries, one at the top and one at the bottom. So we do these 2 rank queries. So corresponding to the top of this interval, where the A is, we would do a rank subscript E. And corresponding to the bottom, or more accurately, just past the bottom, why? Because rank queries are answering how many times does a character occur up to but not including that row. But we would like to include this row, so we have to go one past that row. And so we're doing a rank query down here just past the end of the bottom of that range. And again, we're asking for the rank subscript E. Okay? So let's say we did these 2 rank queries and we got back these answers. That the rank sub E up here was 840, and that rank sub E down here was 843. Well, first of all, how many E's must there be in that red interval? 3, right? The difference between the 2. But not only do we know that there are 3, just based purely on these 2 rank queries, we know which ones they are, because we know they have to be the E's of rank 840 and 841 and 842. Right? They're in order. Right? The ranks are ascending. So if I know that if these are the answers to my 2 rank queries, I know not only that there are 3 E's, I know exactly what their ranks are. Right? So this is what allows us to be able to iterate a step of this matching procedure without ever having to do a long linear scan of that last column. We don't have to do long linear scans. We just have to do 2 rank queries, one at the top, one at the bottom. Okay, so let's run this process. Let's actually do it. for this example. Same example. Okay, so let's start by taking the shortest suffix consisting of just A. And in order to figure out which rows start with A, we actually only really need that C array. So I'm going to actually do all the work here in the skip column. Right? This is where the skip column is where we use the C array. Right? So what's the first element? What's the first row of this range? Well, we have to skip the $sign. That's going to be, so row 1 is going to be the one at the bottom of the range. And what's the row at the top of the range? Well, I have to skip the $sign, and I have to skip all the A's. So the C array is going to give me back 1 and 5 as the beginning and end of my range, right? Corresponding exactly to this range, right? We could describe that range as 1, 5. Okay? So that's the initialization where I'm taking just that shortest suffix and trying to figure out what range of rows start with that letter. Now we can move on to a more interesting part where we're now trying to, given that that's the range of rows that start with A, now we want to find the range of rows that start with BA. Okay, so we want to find the range of rows that start with BA. Here's where we have to do our rank queries, the ones that we were just discussing. Okay, so what are the rank queries? We're going to do L.rank subscript B, since that's our query character, right? B. In row 1, right? That's the top of my range. 1 is the top of my range. 1, row 1. So what's the L.rank B at offset 1? It's 0, right? Because it's how many B's are there up to, but not including that row. And so there's 0. So the answer to this is 0. Draw it in blue. Now let's think about the other rank query, the one for the bottom. Rank sub B at offset 5 now, right? At this row, one past the bottom of the range, right? Okay, so what's the rank sub B here? Well, it's 2. It was 2 B's prior to that. Okay, and so the next range of rows is going to be in the B section. So now I need to calculate the skip required to get to the B section. And so I'm going to have to skip over $sign and 4 A's. So 5. So what's my next range going to be? It's going to be 0 and 2 plus 5 equals 5 and 7. Okay. There you go. And so 5 to 7 is 0, 1, 2, 3, 4, 5. To 7 is this. Okay? Which is correct. That's the next range of rows we want. So there was one step. Let's just iterate this second step now. So let's do the new rank queries. So now we're going to do L.rank sub A at offset 5. So how many A's are there prior to row 5? 1, 2. Running out of space. And we'll do L.rank sub A at 7. That's how many A's are there actually in the entire L array, right? We're down here. This is this sort of imaginary row 7 down here. So we have to do all the A's up to, but not including row 7. 1, 2, 3, 4 is 4 of those. Okay, so 2 and 4 from that. And now we need to figure out how much to skip. We're only, the query character is A this time, so we're only skipping $sign. So the skip is just 1. So the additions we have to do here are 2 plus 1 and 4 plus 1. So we'll get 3 and 5. And these will be our final answers. And so what rows are those? Well, that's these, right? The rows that start with ABA. Okay? So that's the process. Similar in a way to the process of reversing. The trick is to figure out exactly which are the next range of rows that we should iterate to in the next step, we can figure out the answer to that question with just 2 range queries, which in turn is possible because of these wonderful properties of the Boroswheeler matrix. We know that all the results are going to be consecutive. We only need to update the top and the bottom, 2 things. So that is, as long as we can do those 2 things efficiently, then we can do the overall thing efficiently. Okay, so the answer to the count query comes from that final range. I would just subtract to get 2. So here is the algorithm we just talked ourselves through. This is initializing the top and the bottom of the range to be the entire Boroswheeler matrix. This is the loop that progresses along the pattern from right to left, extending the suffix by 1 each time, and doing the skip and rank queries that we know we need to do in each step. Right, so that's basically what I have here. And the key is that this loop is going to iterate for every character of the pattern, right? We might stop early, right? We might discover that the pattern does not occur in the text, and therefore we might eventually find that, and that's what this condition here is for, that top and bot have come together, indicating that the range is empty, and then we can stop. But in general, we'll have to proceed m times, right? P is a length m string. So we'll have to, in m steps, match progressively longer suffixes of the pattern. So how much work are we doing, big O-wise? Well, again, like we just said, that loop may have to iterate up to m times, the length of the pattern. Right? So it's going to have m steps. But that's going to be multiplied by something, right? It's going to be multiplied by how much work we're doing in the inner loop. Okay? So some of the stuff in the inner loop is lookups, very simple, and that's just a decrement. So the complicated part is the rank query, as usual. And since this is a rank query on a string where we're assisted by a wavelet tree, let's assume that we've built the wavelet tree in a balanced way. We have a balanced wavelet tree. Then the rank query, we're doing 2 rank queries, and each of them are big O of log sigma. So there's going to be a log sigma factor here. M steps, log sigma per step. Okay. So that's how we would use the wavelet tree and that sort of skip array, the C array, to answer matching queries and get a count out at the end. But I want to take the conversation just a bit farther because, of course, besides count, we also have this locate query. The locate query being not only where we not only want to know how many matches there are, we want to know where they are. What are their offsets with respect to the original text? And this is kind of an interesting question because we haven't necessarily stored any specific offset information. Right? If we just look at the Boroswheeler matrix itself, right, and just think about the first column and the last column, we're kind of used to being able to do everything we need to do using the first column and the last column. But there's no information here about what offsets these different rotations are, right? We know, there's one thing we do kind of know, which is that that first row, it's going to be the one that starts with the $sign, and therefore the offset of this first rotation is going to be, it's definitely going to be the one that starts with the $sign, the largest one, right? But apart from that, there's no place we can look to directly determine what offset these different rotations occur at. So let's say, though, that we had the task. Let's pick that same example where we've matched ABA. We've done the matching. We have the range. We can, of course, calculate the count from that range. But what we actually want is to get the locations of those 2 matches. Right? This match and this match. Okay. What offsets do those occur at with respect to T? Well, there's a data structure that we could build that would simply pre-calculate that for every row. We could simply, for every row of the Boroswheeler matrix, store an offset, which is that rotation's offset with respect to the original text. And indeed, this has a name, right? That array would be the suffix array, right? The suffix array is, by definition, the array of offsets of all the suffixes of the text, but arranged in alphabetical order, right? Ascending order alphabetically. Okay, so, The first one is 6, which is the largest one because the dollar sign is all the way at the right-hand side and is less than everything else, right? And so on, right? So this would just be basically an array that if we were to store it, then answering these questions would be as easy as doing that lookup and doing that lookup, right? And we get offset 3 and offset 0. So why don't we do this? We don't do this because n integers is too big. We don't want to store an integer for every character of the text. That's way bigger than the Boroswheeler transform, right? Because the Boroswheeler transform is nothing but a permutation of the characters of the text. And let's assume for a moment that the alphabet's pretty small, like the alphabet might be DNA. Therefore, a permutation of the text is no bigger than the text, and the text itself is something like 2 bits per character. Here we're storing an offset, and each offset is going to have to be something like ceiling of log base 2 of n bits, right? And we're storing 1 for every character, so it's going to be a n log n bits data structure. We don't want to store all those integers. So the idea, though, to make this practical will be we don't store all the integers. We just store some of them. We don't store all the answers. We just store some of them using what's called a sampled suffix array. What's a sampled suffix array? It's a suffix array, but where we only keep some, right? So like in this example sampled suffix array here, I've only stored an answer for the rows where the answer is an even number. And for the rows where the answer is an odd number, I haven't stored anything. All right, so I'm, in some sense, saving half the space here. Okay, so now if I go to look up where this one is located with respect to the text, I get a hit. You know, that's included in the sample. So I can just say, oh, that's at offset 0. Great. But if I now go to look up where's this one, I get kind of a question mark, right? That one's missing. So what do I do? Well, so I don't know directly what offset that match is at, but what I can do is just invoke the LF mapping once. The LF mapping is going to take me to a different row of the Boroswheeler matrix, and that row is going to correspond to the rotation that's 1 offset to the left of the one where I started, right? Same reasoning why this is what we did to recreate the original text from the Boroswheeler transform, to reverse the Boroswheeler transform. I'm just going to do that once. So, for example, looking at this A here, it's the A of rank 1, right? There's 1 A prior. So let's just jump to the row that starts with the A of rank 1. That's this row. Okay. So I just jumped to the left by 1 with respect to the original text. But once I get to this row, look what I can do. There's an answer stored for that row in the sampled suffix array. So I can put that information together, right? So when I moved to the left by 1, I found that the offset was 2. So the offset in my original row must have been 3. So I can keep just a sample of the suffix array elements. And as long as my sample is regularly patterned, right, it's at every so many offsets with respect to the original text. In this example, it's every other offset because I kept the even offsets. But it could be every 8th offset or every 64th offset or every billionth offset. Let's say it's every 16th offset. So you could consider 16 to be a nice small number, let's call it a constant. You know, 16 is a constant, then the number of times I might have to use the LF mapping before I get to a row that has a stored element in the sampled suffix array is at least bounded by a constant, right? It might still be plenty of work, but at least it's bounded by a constant. So there's some sort of guarantee about how much work I would have to do in order to recreate what the offset of any of my results is. So this is how the locate query would work. We still have to go through those matching steps, just like we did for the count query, but then there's an extra piece of work we have to do at the end, which is for every row in our range, we have to figure out whether it's in the sampled suffix array, and if not, we have to do some LF mapping iterations to find the offset with respect to the sampled suffix array.